Hello there! Today we're going to be talking about approximating the area under a curve using trapezoids. Now theoretically this should be more complicated than if we were trying to approximate the area using, say, I don't know, rectangles, but if you follow the steps on the screen, I promise it's not going to be all that bad. No matter what kind of shape you plan on using to approximate, you're always going to first want to divide your region into subintervals. To find the lengths of each of these subintervals, you're going to calculate something called delta x, and to do this you're going to do b minus a over n. Here, a and b are the left and the right hand endpoints of the interval, and n is the number of shapes you're going to use to approximate the area. Once you have your delta x, the next thing you're going to do is create a table of values. In this table, you're going to start your x values at a, and then you're going to increase by delta x until you reach b. And to make the rest of the table, of course, you're going to take each of those x values and plug them in to find the associated y values. Next, multiply every y value except for the first and the last one by 2. We do this because when we're approximating using trapezoids, each of our middle y values is going to be a base in 2 different trapezoids, so we have to actually count it twice. Now the last thing we have to do is take all of these y values, the first and the last and the doubled values, and we need to add them all together. And then, to get our final approximation, we're going to multiply our sum by half of delta x. Note that I didn't include the trapezoid area formula anywhere in here. In fact, if you can just follow these steps, you don't even need to know the formula. You can go ahead and look it up on your own time, but I find that the very sight of that formula tends to make people feel intimidated in a skill that's really not so difficult. The last thing we need to know about here is whether or not the estimation we get is going to be an overestimate or an underestimate for the actual area under the curve. Using trapezoids, we're going to get an overestimate if the function is concave up, and we'll get an underestimate if the function is concave down. Great, so no individual step seems particularly complicated here, but I like your style if you don't want to just take my word for it. Let's go ahead and take a look at this example problem here to see how it all shakes out. In this problem, we're trying to approximate the area under f of x is equal to 4 plus the square root of x minus 2 over the interval from 2 to 11 inclusive using 9 trapezoids. We're also asked to state whether our approximation is going to be an over or an underestimate and to justify how we know. And then these cheeky cheekers give the answer away straight off. Note that the function is always increasing and always concave down. Hold on to that information, we'll bring it up again at the end. Okay, first things first, we need to find delta x. You'll see that our interval is 2 to 11 and we want to use 9 trapezoids. This means we can find delta x using delta x is equal to, our b value was 11, minus our a value of 2, all over 9, and this is going to give us 9 over 9, also known as 1. Well, that's pretty nice. That means it's going to be really easy to set up our table here. We start our x values at a, 2, and increase by delta x. So 2 plus 1 is 3, then 4, then 5, then 6, then 7, then 8, then 9, then 10, and of course our b value is 11. Next, we need to figure out the associated y values. So we look at our function 4 plus the square root of x minus 2, and we plug in each of our x values. I just used my calculator. So, without further ado, here's our second list of numbers. When I plug in 2, I get an answer of 4. When I plug in 3, I get an answer of 5. When I plug in 4, I get a slightly more complicated answer of 5.414. And then we continue in this fashion. We get 5.732. Then we're going to get 6. Oh, that's kind of nice, huh? Then we get 6.236, followed by 6.450. When we let x equal 9, we get an answer of 6.646. Oh, that's quite the rebellious 6 there, huh? When we plug in 10, that's going to give us 6.828. And then finally, when we plug in 11, we get 7. Next, we're going to multiply all of the y values except for the first and the last one by 2. This means that the 4 and the 7 are going to stay the same, but that 5 right there has to turn into a 10, 10. 5.414 times 2 is 10.818. 5.732 times 2 is going to be 11. 4, 6, 4. 6 times 2, we know that one, it's 12. And we'll continue on in that fashion. 12.472, that's going to give us 12.9. We also get 13.292. And finally, 6.828 times 2 is 13.656. Now we take our 4 and our 7 and we're going to add them to all of our doubled y values. Alright, I'm going to level with you. I'm a bit tired of listing off all these numbers, so I'm going to let them list themselves out on the screen and maybe come up with a little story for you while you wait. Once upon a time, a long time ago, there was a man named Isaac Newton, and he supposedly invented calculus. Around the same time, there was a man named Gottfried Leibniz who also invented calculus completely separately from Isaac Newton. Upon discovering this crazy coincidence, the English and the German mathematicians duked it out in history's nerdiest fight, trying to take credit for which mathematician actually invented calculus first. Historians tend to agree that Newton may have invented calculus first, but Leibniz's notation was a little bit better. And all that history has brought us here. When you add all those numbers together, you get 107.602. To find our final answer, what we need to do is take this value and multiply it by half of delta x. If delta x is equal to 1, then that means that 1/2 of delta x is equal to half. Very easy. Therefore, the area under f of x from 2 to 11 is approximately equal to 1/2 times 107.602, which gives us about 53.801. Boy, that felt like a lot of work, but it was a lot of trapezoids. Now, we also need to answer the question, is this an over or an underestimate? And again, our function is always increasing, and it's always concave down, and that's the one that we're actually interested in. Our explanation is at the bottom of the screen here. Since f of x is always concave down, the trapezoid approximation is an underestimate. So the actual area under the curve from 2 to 11 is greater than 53.801. By how much, we don't really know, but to be honest with you, it's probably not that much more. And that's it. All we had to do was find delta x, set up our table, find the associated y values, double the middle y values, add all of those y values together, and then multiply by 1/2 delta x. If we want to know whether or not our approximation is an over or an underestimate if we're using trapezoids, we look at the function's concavity. Since this one was concave down, we had an underestimate. But if it was concave up, we would have had an overestimate. Right, that's all I have to say about this for now. Make sure you're getting plenty of practice because that's the only way you're going to get these steps all the way down. And with that, I bid you adieu. Thanks for coming and we'll see you next time.